Hey, so welcome back. In the last video, we looked at masking and partition M files. So now that we have those things taken care of, we can move on to the next part, which is to select the slice of interest. So let's go ahead and open up the slice select M file. So let's look it up onto your left. Slice select.m file. Okay, so this is where you extract the slice of interest. So just think of the MRI data now partition is a volume. Think of it as a three-dimensional volume. Um, uh, yeah, it's just a three-dimensional volume. You basically can select a slice in that volume, and that volume is changing over time. That's where you have four dimensions, right? Just think of that in that way. Maybe that'll help you uh, process this tutorial better. So basically, we select the slide interest based on the user's defined slide selection, the end slides. So here in the main file, we define the end slice to be the third slice, right? So that's end slice. And then we also want to take out the copy of the magnitude file, the original copy, where it's not processed, to be defined to this variable called mag and copy. And then again, to save some memory, we clear some of the handles, unnecessary handles. We basically store everything in this variable called MRI and clear the individual variables you see. And then here's the error message if there's not enough input. And that's part of the switch function. So once you extract the end slice, we're ready to move on to the next function. Okay, so the next function is that now you have the cross section is now an image file that varies over time. So this the dimension of it is still 3 dimension because it's d1 times d2 times the number of cycle. So that's why it's three dimension. We pick out this slice, so we take out 1 dimension. So instead of 4 dimension, now we have 3. It's d1, d2, and the cycle. So 2 spatial dimensions and 1 temporal dimension is left. Next, we need to look at we need to calculate the phase change based on those values, those files we calculated earlier. The slice selected. So let's open up the shave angle.m. Shave angle.m. Of course, you cannot find it because it's actually a phase calculate. My mistake. It's phase calc right here .m. So open this up. So earlier we store all of the stuff inside this variable called MRI, and now in this M file we basically assign a local variable called magnitude real and imaginary, so it's easier to process here. And we use an equation to calculate the phase based on the real and imaginary information, and we do throughout from cycle equals 1 to the last cycle, which is 150 in this case. And this equation right here to calculate the phase is based on the Handbook of MRI Post Sequence, page 560. And this is how you calculate the phase. And the output's going to range from minus pi to pi. Okay, now we have the phase angle. It's variable is called A. We want to filter it using the masking, the mask that we created earlier. So that's the mask. We multiply with the mask to get rid of the background, and we call this shave angle. So this is the face information without the air information, air background that is. And then we clear the handles again, and then print out some debug messages. And then of course, if there's not enough argument, not enough input, then we're gonna output an error statement here. So that's pretty much straightforward in terms of like what's happening here. I can understand if you don't understand this part, because if you don't have the book, then it's gonna be really hard to understand this part. But just thinking in terms of blocks, functional blocks. So I have this equation that can that gives me the phase information if I give it the real and imaginary information. All right. Again, I want to stress this out. Earlier we have 4 dimensions, 3 spatial dimensions, 1 temporal dimension, and we extracted the nth slice, which is the slice the user wants to look at. So that means when we select that slice, we ignore other slices. So now we only have 2 spatial dimensions and 1 temporal dimension. So that's where you have D1, D2. There's no D3 anymore. Now, but you still have the number of cycles. That's the 3rd dimension. Okay. So now we need to calculate the temperature change. So let's go ahead and open up the calc delta T. So from this point on, we only care about the end slice, right? We're not gonna have to worry about other slices unless we change it here. So all the calculation following this is just based on the 3rd slice. Okay, open up calc delta T. Here. This is pretty short. So to summarize all of this without looking at the detail, it's basically I use the phase and multiply with a constant to give me a delta change in temperature. That's the simplest in a nutshell, basically. But if you want to look at in detail, then these are the parameters you need. This is the proton gyromagnetic ratio. B is the magnetic field strength in Tesla. Alpha is the thermal coefficient. That is the calibration fudge factor, if you will. We all need a fudge factor for when you calibrate something. So that's the thermal coefficient. Constant D is basically it's a constant, so I basically lumped up all the parameters, including echo time. Echo time is one of the inputs here. We defined earlier before the initialization function. We defined the echo time. Remember that? It's back here. T right here. So go back to calc delta. So I lumped it up into a constant. So this is a constant. So basically you have your delta phase, which is change in phase, divided by this constant. It will give you the chemical shift. Lambda times B times Te is the chemical. Delta phi divided by these values gives you the chemical shift. That is something else if you want to look at chemical shift, but for now, just ignore the chemical shift for now, okay? The change in temperature is defined as the change in phase divided by this constant right here, okay? And this constant right here is basically lambda beta, B is beta, Te times alpha. So again, change in phase divided by this constant, and this equation is in the paper, some reference papers, to give you change in temperature, and it's going to output some messages to the user. So, yep. So not too complicated. as far as the algebra goes, but the physics behind this you need to go into the reference papers to look at. Okay, so once we calculate the temperature change, we can go ahead and read the optical sensor data, which is nothing too crazy here. I mean, it's just a text file, and you're just reading off that. Basically, let's go ahead and open up and see what's in there. Re-op. So basically, open up the file for reading, and then you can define use text scan, and starting at row 23. Let's open up the file so it makes more sense. Where's the documents? See that? So 23 is where you want to start off with to extract the headlines. And this can sometimes like depend on like the comments section. This is gonna change and then output an error. So be aware of that. And you can always change the starting point by changing this number right here to whatever the row the headline starts at. Okay. So here is where um, we extract the information and basically find the change, the delta in temperature, not the absolute temperature, but the delta, and then basically extract that using this. And I average in this example, I basically averaged two channels together and give me the change in temperature here. Just some special cases when there's no signal, then I just make a zero, plug in a zero in there. And sometimes there's like some missing data, there's not enough uh, readings for some reason, then that's going to output an error for you so you know. In that case, you can just like plug in a value similar to the previous value just to make this thing plot. That's not going to change much. But yeah, that's all there is to this part. It's not too crazy. Here is the part where it checks for the length of the optical sensor data versus the MRI data. Make sure they have the same number of rows. Yeah, okay. Okay, so that is it for the basic startup of this processing script. The next part is where you have to do the analysis and plotting, and we'll save that for the next video. Alright, I hope I wasn't being too ambiguous, I guess.